Hey guys, it's so this is for Thursday, and I have my tea here. Trying to keep my sinuses nice and clear. Um, and today we're gonna learn about 14.9, which is the effect of structure on. I mean, it says acid-base properties. It's really just acids. Like um, that's what we're talking about here. And I want you to keep in mind two things. It's actually like a pretty quick lesson. So, firstly, there's electronegativity is going to play a role. Polarity of the bond and strength of the bond. And something that's not in your book, though I don't think I saw it, was organic acids. So we're gonna hit these topics and just kind of talk about. There's sort of like there's certain examples that will fall into these categories. So we'll just first start off with electronegativity, and I'll keep these up here so I don't forget these things. But when they talk about electronegativity, we're usually talking about going across a period. And what you're doing with increasing the difference of electronegativity is you are increasing the polarity of the bond. So if you went across and did NH3, H2O, HF, like you went across a period and you looked at H's attached to these three things, you would see that your electronegativity difference increases, and therefore the strength of the acid increases. Even though HF is considered a weak acid, HF, the electronegativity difference is so strong here that it's not easy, but when you put it with water, for some reason, the H can be donated to a water, whereas in H2O, you know what that is, it's really low. And then NH3 is more of a base, so it's not really, I mean, though it can act as an acid depending on what it's with, it's probably not going to react that much towards an acid. So as your electronegativity differences increase, the polarity of the bonds will increase as well, and it'll make it easier for the H to kind of come off of, like, to pop off and attract to a water molecule. Okay? So, but that's only across a period. So that means, like, if I was looking at like H2S and HCl, I mean, you guys already know that HCl is your stronger acid, but it's based on the electronegativity differences. So that's only really across a period. Okay, now here's the odd piece: is as you go down a group, and these are usually just for like binary acids. So that last one was really for binary acids as well. I should actually put in here oxo acids. So binary acids, if we were comparing HF, HCl, HBr, and HI, as you go down group 17, you should know that HI is your strongest of this. And HF, even though it's a really polar bond, is actually a really small couple of atoms. And small couple of atoms means the atoms can get really close to each other. So small atoms have a short internuclear distance, and that usually leads towards a strong bond. So even though HF is really polar, of all these, it's the most polar. It's the weakest acid because the bond strength is so high. So it's not likely for H to be protonated onto a water. Whereas these three things, in fact, HI will be your strongest. The larger atoms have weaker bonds to H, making it more likely for H plus to kind of pop off and leave an I minus. Also, kind of a side note is the larger atoms. Also, larger negative ions that are the conjugate bases are stable in solution. And what that means, it's kind of like, all right, if I have an I minus versus an F minus, okay, I'm just doing size, thinking like I minus is going to be enormous, F minus is going to be really small. This has really small electron density. Or sometimes you'll hear it, let's actually write it as charge density. And the way I think about this is, okay, if an H plus was kind of bouncing off these things, it's very unlikely to be attracted to an I minus. And so, because the charge density is spread out over a huge area, it's kind of like, where would the H plus attract to if the negative charge is so big and diffuse? Whereas in this one, the charge density is actually really high. Charge density is high. And so you can kind of think like, okay, that negative charge is just kind of really, really tiny and easy to pick out. Like, oh, I know where the negative charge is. And so an H plus will just kind of like pop on there real easily. Whereas these ions, the Cl, the Br, and the I, tend to be really stable in an aqueous solution because their charge density is so low. The charge is so diffuse. Okay. Okay, so there's your strength of the bond. Okay, now let's talk about oxo acids. So those were really mostly just binary acids. The oxo acids are one in which you have an OH bond somewhere, right? And this is the bond that you're interested in seeing if it'll break. So that's your bond to break. Ooh. All right. So there's two scenarios that you'll have here. I put them both on your quiz and on the review sheet. So if you have more oxygens, so let's take, I'm not going to draw like the whole Lewis dot structure, but there's H2SO4, and so one of these H's is going to come off. And since there's so many oxygens are really electronegative, super highly electronegative, and what they do is they pull on the electrons of the sulfur, which then in turn makes sulfur really positive, and sulfur will end up pulling on the electrons of both of those, not only this bond but that bond as well, and it's going to weaken that bond. So once that bond is weakened, it weakens the OH bond. It makes it really easy to come off. And what happens is if you decrease your number of oxygens, you're going to make the acid not as strong because it's not pulling the negative charge away from the sulfur. So less oxygens will mean weaker acid. So if I was comparing like H3PO4 to H3PO2, and I said, what is your stronger acid? Even though both of them are weak, this is your stronger acid, because those extra O's will pull electrons away from the phosphorus, which in turn will pull electrons away from the OH bond, weakening the bond. Okay. And then the other part, so there's two things. So first rule of oxoacids is if you have the same central atom, the one with the less oxygens will be the weaker acid. So same central atom, the one with less oxygens will be the weaker acid. If you have the same number of oxygens but different central atom, okay, I'm going to leave that rule up there just so you can kind of compare it to this one. If you have the same number of oxygens but different central atom, the highest highest En of central atom will be strongest acid. So that means if I was comparing like H2SO4 and H2SeO4, if you remember your trends from electronegativity, Se is lower than S on the periodic table, therefore its En is lower, and it's kind of the same rule, like it's not going to pull as hard on the electrons of the OH bond, and therefore this is going to be stronger. Sulfur has higher En and will pull on electrons from OH bond, weakening the bond more. Ugh, that doesn't look like weakening. Weakening the bond more than Se will in H2SeO4. Okay. All right, and then the last piece, I don't believe organic acids are in this particular part of your book, but I just wanted to describe that real quickly. Okay, organic acids. So you probably remember from Enriched, organic acids have this C double bond to an O with an OH group. And if you think about, so whatever this thing is, like R just means like any carbon chain existing here. And if you react it with water, this H will be attached, and then what you'll form will be, you'll end up with a negative charge plus H3O plus, and now we're kind of calling back resonance here. So this ion is will have resonance, and they use this term called resonance stabilization. And what that means is that this C double bond to an O will actually, C double bond to an O with another O, these electrons will actually, in resonance, will actually kind of share this double single bond. In fact, if you remember this correctly, those, like wherever the bonds are shared where there's resonance, each one of these bonds is equal, and it's a 3/2 bond. And so now you have, there's your two resonance structures that would occur, where the negative charge is there, and now you've done something kind of fancy. You've decreased the electron density. And by doing that, you make it hard for a hydrogen to attach to somewhere on this leftover negative ion, making it unlikely to go and reform the organic acid. And that, it's not saying that the organic acid is all that strong, it's just that the organic acid even exists. It's mostly because when it does deprotonate and it drops this H over to H2O, that ion is not as likely to attract back an H and reform it, because the negative charge is sort of spread out along the whole right side of the ion. You know, like there's almost like no spot for the H to attract there. Now, it actually does attract and reform this. I mean, it is an equilibrium. It's a weak acid, but that's the reason why it's an acid. Okay, so your homework is basically just to finish the test. If you did a few questions about, I think I put like one more thing on here. Let me write this up real quick. So the last little piece is, it's almost like I could just write it for you, but I'll just say non-metal oxides are considered acidic anhydrides. What they do is, like, when reacting with water, they form an acid. So it behaves as an acid, so like carbon dioxide, N2O, etc. And then metal oxides are called basic anhydrides. And these ones, when they dissolve in water, they produce hydroxide ions. So when reacting with water, they produce hydroxide ions in solution. And so, literally, name any metal oxide, like barium oxide, calcium oxide, magnesium oxide. You put those in water, they'll form bases. Okay, so good luck on your quiz. It's due Friday night. I should have them back to you by, Saturday, Sunday. It shouldn't take too long. I really mimicked the review sheet. So if you spend a lot of time on the review sheet and you watch the harder questions from what I went through on YouTube, you should be pretty well suited for doing well on the quiz. It shouldn't take you too long. So, but hey, all the best. Miss you much, and I will see you soon.